Special relativity theory, derivation of time dilation. Key statements. 1. Frame of reference. Frame of reference is the coordinates that describe the position of an object. Sets of coordinates, space and time coordinates. X, Y, and Z are the space coordinate and T is time coordinate. Number 2. Initial frames of reference. It obeys Newton's first law. Objects won't accelerate unless they are acted on by external force. Stationary and constant velocity, no acceleration. Number 3. Inertia is a property of matter by which it remains at rest or at uniform motion in a straight line unless acted upon by an external force. The inertial mass of an object is its tendency to resist changes in velocity. Number 4. Einstein's theory of special relativity only works in inertial frames and is based on two postulates. Postulate means assumptions. A. The law of physics is the same in all inertial frames. B. Speed of light in free space, which is vacuum, is invariant. Invariant means same or constant for all inertial observers or sources. If you have two inertial frame of reference, S and S prime, each frame of reference has its X, Y, and Z coordinates, where X is parallel to X prime, Y is parallel to Y prime, and Z is parallel to Z prime. So this is Y prime, and this is Y. This is X prime, and that's X. They're parallel. And this is Z, and Z prime. Both starting from the same point, 0 or 0 prime. S has an observer A, S prime has observer B, and there's a clock on both frame of reference. If the S prime frame of reference travel with a velocity v, moving in a uniform motion or constant velocity with a speed close to speed of light, where t is not equal to t prime, two physical events of light bulbs at different time A and time B from the same location from S prime, looking at the event from S frame of reference XA and TA, XB and TB, where A is the time the light bulb goes off and B is the time the light bulb goes off at the same position. X in this case is XA and XB from S frame of reference. From S prime frame of reference, you have XA prime, TA prime, XB prime, TB prime. You do know that XA prime and XB prime are equal because they're in the same location. So the XA prime is equal to XB prime. Using Newtonian, TB minus TA will be equal to TB prime minus TA prime. In this case, the speed is going to be very slow, but for special relativity, TB minus TA will not be equal to TB prime minus TA prime because the speed is very fast. The speed is close to the speed of light. Relativistic time, which is delta t, equals TB minus TA because that time is relative to the S prime frame of reference from S. Proper time or rest time is delta t naught, which is equal to TB prime minus TA prime because this is the true time from the observer B in S prime frame of reference. Applying Lorentz transformation, where S, the inverse Lorentz transformation or reverse Lorentz transformation, where X is equal to gamma open bracket X prime plus VT prime close bracket, where Z is equal to Z prime, Y equals to Y prime, T equals to gamma open bracket T prime plus Vx prime over C squared close bracket. For S prime, the Lorentz transformation X prime equals to gamma open bracket X minus Vt close bracket, Z prime equals to Z, Y prime equals to Y, T prime equals to gamma open bracket T minus Vx over C squared close bracket. Consider a physical event from the rest frame of reference S, where T from reverse or inverse Lorentz transformation equals to gamma open bracket t prime plus vx prime over c squared close bracket. At event A, we get ta with gamma open bracket ta prime plus vxa prime over c squared close bracket. At event B, we get tb, also the same with b. Now we measure the time difference between the two events, ta and tb, where tb minus ta is the delta t, which we call the relativistic time, and we substitute tb and ta into the equation, and we get delta t equals to gamma square bracket open bracket tb prime minus ta prime close bracket plus, well, v over c squared is common from both, so we have v over c squared open bracket x prime b minus x prime a close bracket close square bracket, but xb prime equals xa prime. Therefore, xb prime minus xa prime equals to 0. Therefore, delta t equals to gamma open bracket tb prime minus ta prime close bracket equals to gamma delta t naught. Delta t equals to gamma delta t naught. Delta t equals to, well, gamma is 1 over root 1 minus v squared over c squared. Gamma is Lorentz factor times delta t naught. Delta t is equal to delta t naught over root 1 minus v squared over c squared, or delta t equals to open bracket 1 minus v squared over c squared close bracket to power minus a half times delta t naught, which means that delta t is greater than delta t naught. So that means delta t is longer, delta t is stretched. Delta t takes longer time. This is time dilation. A moving clock runs more slowly than a stationary clock. Delta t is the stationary clock and delta t naught is the moving clock. So this one, delta t, is bigger than delta t naught. Question: the half-life of charged pi mesons at rest is 18 nanoseconds. Calculate the half-life of charged mesons moving at a speed of 0.95 speed of light. Solutions: T naught is equal to 18 nanoseconds. The velocity is equal to 0.95 speed of light. This is the velocity of mesons. Therefore, the ratio of velocity to the speed of light by dividing both sides by c is equal to 0.95. Using the time dilation, that implies t equals to 18 nanoseconds over root 1 minus 0.95 squared, because v over c is equal to 0.95, and that equals to 5.76 times 10 to the power minus 8 seconds, which now equal to 58 nanoseconds. And this is the time relativistic from the stationary observer, which is 58 nanoseconds. So the half-life at rest is 18 nanoseconds, but when it's moving with a speed of 0.95 speed of light, the half-life then changed to 58 nanoseconds. That time has dilated. It gets bigger. It takes longer.